screen? Awesome. So hi, my name's Charlie. I work at Astral. We build developer tools for the Python ecosystem in Rust. So we're best known for two tools, the first of which is called Rough. Rough is a Python linter and formatter. So in the Rust ecosystem, the analogous tools would be like Rust Format and Clippy. And then we also build a tool called UV, which is what I'm going to be talking about today. UV is a fast, all-in-one Python package manager. So you can use UV to install Python, create virtual environments, resolve dependencies, install packages, build packages, publish packages to the registry. If you've worked in the Python ecosystem at all, you might be familiar with tools like pip, pipex, PyM, virtualenv, poetry. UV is really designed to be an alternative to all of those tools, not to any one of them. So a framing that I sometimes use is we want UV to be this single binary that gives you everything you need to be productive with Python. So you curl install UV, and it just drops you into this pit of success in terms of you don't have to worry about how do I install Python, what's Python versus Python 3, what's pip versus pip 3, how do I manage all these things that are installed on my machine. So UV does a lot, and it does it while being a lot faster than a lot of the other tools in the Python ecosystem. And when we started working on Package Manager for Python in particular, I anticipated some of this, which is, okay, there's like so many different tools that have tried to take on Python packaging. What makes you think that like what the ecosystem needs is just one more tool? And I am naive enough to actually believe that what we are doing is pretty different from a lot of the efforts that have been made before in Python for at least two reasons, and they tie back to why I'm here talking at a Rust conference. The first is just the scope of what we're trying to build. Python tooling is very fragmented. So like any workflow that you want to do in Python, you typically need to chain together like a bunch of different tools. And for any step in that workflow, you have a bunch of different options for like what tool you use. With UV, we're trying to build this unified stack. So UV is not like built on top of anything else. It is, pure Rust. And we build everything from our own like resolver to dependency installer, virtual environment manager. We've re-implemented all these Python standards and specifications from scratch in Rust. So I see UV as this sort of new take on Python where we're trying to build a very unified set of tools. And it's very much inspired by the experience that we have in Rust, right? Rust tooling is like this very high confidence endeavor where if you clone a project, you're pretty confident that you can figure out how to run it and that you can run and build it successfully. And that's sort of what we're trying to get to with UV. The second is just performance. I like building very fast software. I think it's extremely fun, but it's also very impactful for users. And one thing that we've observed in the tools that we've built is when you have tools that are like way faster than other tools, it really changes like the user's relationship to the tool and the way they work. So like in Rough, for example, we've talked to companies where their whole linting pipeline used to run on CI, and it was this thing that everyone hated because it was always blocking their PRs. And we give them a tool that's fast enough to run as like a pre-commit hook or even on type. And so suddenly it's this tool that's actually like helping you write much better code and ship much faster. So like I said, everything we build is powered by Rust. And I think, in my opinion, there's at least some evidence that this like different vision for Python tooling is working. We have UV, this is just UV, not including Rough. We have a lot of GitHub stars, we have a couple hundred contributors, but we're also closing in on like almost 30 million downloads a month. And this is a tool that we released in February, so it's like 6-8 months. And I think the most shocking statistic that I've seen is that over the past 30 days, so 13% of requests to the Python package index came from people using UV. And the Python package index serves like 2 billion downloads a day. So that's like 250 million downloads coming from people using UV. And I include this stuff because like this is not a science experiment, right? Like this is something that's making this is like a big Rust project that we shipped that's making a big impact on a totally different programming community that just a lot of people are using. And in sort of thinking about how to frame some of the challenges that we've faced in building UV, there was this interesting question that came up, which is just if you're such a big fan of Cargo and of Rust tooling, like why not just frame this as like rebuilding Cargo? Like even more superficially, why don't you just like fork Cargo and swap out the index to hit PyPI instead of crates.io or whatever. And of course that won't work, right? Because Python is not Rust. I don't think I have to convince people here of that. But I want to talk through like a couple of the things about Python and Python packaging in particular that are different than how things work in the Rust ecosystem and some of the problems that they have caused in trying to build a package manager. So the first is that Python does not have any multi-version support. So you cannot have two versions of the same package installed at the same time. So if we have a package that depends on a specific version of VLLM and a specific version of LangChain, these are just two popular packages for working with language models. Maybe the version of VLLM requires Pydantic 2, but that version of LangChain does not support Pydantic 2. So in Rust, this is actually a solvable graph because Rust is allowed to pull in multiple versions of a single crate in its resolution in the graph. But in Python, it's not. Like, this is not a graph that can be solved. You cannot satisfy this set of dependencies when you're trying to resolve a Python project. So instead, what you might do is you might go to the user and say, actually, you need to like lift the restriction on VLLM. And maybe they say, OK, I'll accept any version. And we're then responsible for going through and testing all the different VLLM versions, and maybe we eventually find this much older version that does work with Pydantic 1. And this resolution is okay, we can actually satisfy this. But going through and solving this set of constraints and testing all those versions can be very slow and fairly expensive. And the thing to realize is like, this is not the complete graph. Like if you just depend on these two packages, VLLM and LangChain, you end up with something, this is just like a subset of the whole graph that you have to solve, right? And Cargo has to do a similar thing. Cargo does have to figure out a set of dependencies that satisfy the constraints that you give it. But Cargo does not have the exact same formulation of this problem. Cargo is not required to find exactly one version of each package that helps you satisfy the graph. So Cargo, while it still has to solve a problem, is solving a much less constrained problem. And this version of the problem, where you need to satisfy all the dependencies and you can only have exactly one version of each package, is NP hard, which is very hard. So the first problem that we run into that's pretty different from how things work in Rust is we don't have this multi-version support, which gives us an NP hard constraint satisfaction problem that we have to try and solve as efficiently as we can. The second is that Python has this very rich syntax for filtering your requirements by platform. So in Python, you might see a set of requirements that look like this. It's just a bunch of packages at the versions that you're allowed to include them. And then at the end, we have this identifier on the right, which says that import lib should only be installed if the user is running a version of Python prior to 3.10. And if we look at some of the like transitive dependencies, maybe we see, okay, we also need to include the Colorama package, but only if the user is on Windows. These markers, there's like a whole grammar around them too, so you can like and or them. And this by itself is not very different from what we have in Rust. Like you can have conditional dependencies that are conditional on platform. But the thing to keep in mind is that when we're dealing with this grammar and all these conditions, we have to take them alongside that single version constraint. So if the user gives us dependencies that look like this, they're asking for Pydantic 2 on Windows and Pydantic 1 everywhere else. It's a little bit complicated because this actually is a satisfiable graph, even though they're asking for two completely distinct versions of Pydantic, because we know that a machine is either like Windows or not Windows. Right? That condition, those conditions on the right, they can't both be true at the same time. So we have to think in terms of how do these markers work in their relationship to one another. So as like a counterexample, this we cannot solve because on Python 3.12 or 3.13, the user would be asking us to install both Pydantic 2 and Pydantic 1. So this we need to reject. And if you think about what's happening here, we have these two requirements for the same package, and we're looking at these markers, these environments on which the user wants us to install them. And if you think about these as marker A and marker B, when we're trying to figure out if this is okay, the question we're asking is, do A and B overlap? Do those marker expressions overlap? Which could also be formulated as, can they both be true at the same time? which can also be formulated as, are they disjoint, which can also be framed in terms of a Boolean satisfiability problem. So is the expression A and B satisfiable? Is it possible to satisfy that expression? And when you hear the term satisfiable, you should be very worried, because this is also NP-hard. Deciding whether two marker expressions are disjoint is actually an NP-hard problem. And it looks really easy here, because it's just windows and not windows. Like, of course, those are disjoint. But in practice, when we solve complex graphs, we end up with lots of very large markers. This is from solving transformers, which is a really popular Python project. These are real marker expressions that end up in the lock file by way of trying to solve the dependencies there. And these are actually like fully simplified and normalized. If you do not apply extremely rigorous simplification to these, they can be tens or hundreds of kilobytes large in terms of the expressions that you start creating. So we don't have multi-version support, which makes solving much harder. We also have to do all this sort of algebra on the environment markers and the support and the ands and the ors and that whole grammar, which also gives us like a totally separate set of NP-hard problems. I want to talk about a few more issues more briefly that thankfully are not NP-hard, but still cause some trouble. So one is that in Python, when you're working with third-party packages, a lot of the time you're not actually like interfacing with Python code. So if you're using like NumPy or SciPy or something like that, those are all written in in like C or C++. They're written in native code and then compiled and exposed through Python. So there's a lot in Python standards and in the ecosystem around enabling people to pre-build those distributions. Like when they go to publish a new version of NumPy, they don't just publish the source code, they also publish builds for Windows, for Linux, probably at a bunch of different glibc versions. They might have to also multiply that by the number of Python minor versions they support. Like some packages might have like 70 or 100 or more artifacts for a single release. And the other thing that the other problem that this causes is that sometimes these distributions are really, really big. So PyTorch, for example, is like 500 megabytes. So whenever we're interfacing with these artifacts, we have to be very careful about how much work we do and how we do it, because they can just be huge. I think the thing that causes me the most frustration is in Python, packages are not guaranteed to have statically defined metadata. And like knowing a package's metadata is extremely important because you need to know its dependencies. Now, most of the time, a package will include its dependencies in a statically defined way, but it is not required. And in the worst case, what you actually have to do is you have to clone that Python project, run some arbitrary Python code, and get it to interrogate the dependencies and pull them out. So in the course of resolution, you occasionally actually have to run Python source code for projects that the users depend on. Another one, which is a little bit more superficial, but when projects do have metadata, it's serialized as email headers. And this one I just include because what we see here is an ecosystem that's evolved, often organically, over decades, right? And it's easy to sit here and laugh, and it is kind of funny, right? Like, why would they do it that way? Why would they use email headers? But at the time that behavior was specified, like JSON did not exist. And so for me, when I see this set of problems, the right response is really to be curious about it, which is to say, like, what can we as a Rust ecosystem learn from what worked in Python and what's been hard? And then I sort of straddle the border here. So what can we as a Python ecosystem learn from Rust? What can we take from Rust and bring back to try and make Python better? This is like one of, if not the most popular programming ecosystem on Earth, right? Like building for this ecosystem is very high impact. And so our approach is like take these problems, take them seriously, and then try to solve them in like new and different ways, often inspired and powered by the experience that we have with Rust. So I mentioned Rust a lot. UV is written in pure Rust. And when I think about like why Rust is important or helpful for the project, there are really like four things that stand out to me. So the first is safety. This is perhaps an obvious one, but when I started learning Rust, I actually didn't care at all about memory safety. I did not understand why it was important or even really what it was. I had no systems programming background. I now think that memory safety is actually very underrated because I suspect there are a lot of people who think like I did when I started learning Rust. And we've now shipped 2 very large projects to millions and millions of people, millions and millions of Python users. And to the best of my recollection, I don't think we've ever had a user-reported issue that was caused by a memory problem, which is kind of crazy. Like the lower bound on quality of software that we can ship with Rust, assuming we stay within the bounds, is super high. And for me, that's like, when we're building tooling that's, I'm not gonna call it like mission critical, but it's like stuff people are using all day, right, throughout their day. Building reliable software is incredibly useful. The second is portability, and I'm like sort of misusing the term because I want to describe something fairly specific, which may sound very obvious to people who work in Rust, but with Rust, we can build binaries that users can download and run on all sorts of different platforms with no external dependencies, right? That's actually a super useful property because what it means is we can tell users to download and install UV, and we can then install Python for them. We're not building a tool that depends on them having some other tool chain or some other set of dependencies installed. And this has really been pretty game-changing for people in Python. Like, they no longer have to worry about, how do I brew install Python? How do I do X, Y, or Z? They can just install UV, and we can kind of take everything from there. There's no additional setup or bootstrapping necessary. I also think a lot about accessibility of the language and the ecosystem. We have, like, across Rust and UV, I think we have like over 700 contributors. And a lot of those are people who at least claim to be writing Rust for the first time. It's a lot of people who come from the Python ecosystem and they want to find a reason or a way or some entry point into Rust. And when I first started the project, this was a very common critique, which was, this project's never going to work because you're never going to be able to build a community around it because all of your users can't contribute and can't work on the project. And I think that's actually been like very disproven by the way that we've seen the community build. I think Rust is a hard language to learn. I do not think it's the right fit for every project. I don't know if that's controversial or not. But like the tooling, the resources, the ecosystem have made it into a very accessible systems programming language. Like I said, I had no systems programming background prior to learning Rust 2 years ago. Part of the reason I started working on Rust was because I wanted to learn and get better at Rust. And now, we ship these things that a lot of people are using. So for me, I think I really admire the way that Rust has made building this kind of software accessible to software engineers. And then the last is performance. There's a lot to say about performance, and I will talk about it, but I think the way that I've come to think about Rust and performance is Rust gives you, a high baseline for how fast your programs will be, and then it gives you all the tools you need to build really fast programs and forces you to care about a lot of the details that matter when you're trying to write really performant code. For example, allocating and managing memory. Allocating memory is relatively slow. Rust forces you to really think about where you're allocating memory and how are you using it. So I want to spend the rest of the talk just talking a bit about some of the things that we do in UV to make it fast for 2 reasons. One, I think it helps demonstrate like some of the strengths of Rust, but also I just think it's kind of like fun and interesting, and I like talking about like specific examples because they're very cool. So let's talk about version parsing. In Python, as in most ecosystems, packages have versions, right? So a package could be version 1.0.0, but it could also be like 2.3.1 beta 1. So this would be a pre-release. That can be beta, alpha, or RC, and the pre-release itself is version. So you can have like beta 1, beta 2, beta 3. You can also have development releases, which are somehow like slightly different from pre-releases. It's a totally separate tag. You can have post-releases. This is typically used for like documentation updates or other non-code updates to your packet, to your project. The spec also makes room for something called a local version identifier, which is this piece that goes after the plus sign. This has become very popular because of gaps in the standards, especially around like CUDA and building for specific accelerators. So like PyTorch uses this a lot. If you've ever worked with PyTorch, you might see this, but it was not intended for that purpose, but it's sort of how it is used often now. I think the most obscure is you can have this like this number followed by an exclamation point at the front. This is called the epoch. This exists I've never actually seen this in the wild, but it exists for largely for compatibility. At the time that the spec was introduced, they wanted to give people a way to sort of like shed their old versioning schemes and declare that some new version was actually the latest version. And of course, all these things can be combined. So like this is a totally valid version. You can have like an epoch. You can have as many release segments as you want. It does not have to be like 1, 2, or 3. And yeah, you can have, what is it? You can have, I won't be able to say it. It's like a post-release. It's a dev release of a post-release of a pre-release with a local version segment. So anyway, if you want to represent like the full space of valid versions, you need like a fairly heavy struct. There's a lot of different fields. There's like 2 vectors in here. And in the course of doing like a big extensive resolution, we actually create like hundreds of thousands of these. And the thing that we realized, well, not me, but Burnt Sushi did, is most versions are actually very simple, right? Like the versions I'm showing here, like how, like that, like I cannot imagine a project would actually publish that. Most versions look like 1.0.0. And in fact, it turns out that we can represent most versions with just a single U64. Not all, but most versions. So the way that we use that representation is that given a U64, we have 8 bytes, and we use them very judiciously. So bytes 6 and 7 represent the major version. The major version gets 2 bytes because calendar versioning is not uncommon. So like 2023 would not be a crazy major version to see. The next 3 segments each get 1 byte. And then at the end, the last few segments can represent either a pre-release or a post-release, right? So there's a lot of versions that we cannot represent this way. Like we cannot represent versions that have more than 4 release segments. We couldn't represent anything with like that local version identifier, anything with an epoch. But like over 90% of versions fit this scheme empirically. But the really cool thing is that the way that this is designed means that greater versions map to larger U64 integers. Because not only are we like creating these all the time, but we're comparing them constantly. Like we're saying, is 1.0.0 larger than 2.0.0, right? Like things like that. And if you have 2 of these versions that are represented in that way, that comparison is just comparing 2 U64 numbers. Like it's extremely cheap, as opposed to trying to compare that big struct we looked at before with a bunch of vectors and very complicated rules around how they interact. So most of the implementation of this is actually like a huge comment explaining what I just walked through. But it is a real thing that we did, or that Andrew did. At least in this example, where it was a really complicated resolution with all the very minimal I/O because all the data was cached locally, it sped things up like 3 or 4x. Like we were just spending a ton of time dealing with versions. Often this is actually the best way to solve a problem sometimes, is just to convince Burnt Sushi that it's really interesting and worth working on because he sort of comes out of a cave with something like this. A lot of what we do in a package manager is I/O. We're like downloading packages, we're unzipping them, we're like making network requests to get metadata. And in particular, we make a lot of like very sort of constant small network requests because we do a lot of prefetching. Like if we know you're going to rely on these versions, we might go and ask for them from the registry because those requests tend to be fairly small. So UV is written entirely in async Rust. It's built on Tokio. And counterintuitively, we use the single-threaded runtime, and all of our I/O happens on a single Tokio thread. And empirically, what we found is we actually don't perform like, in a relative sense, a lot of what we're doing is I/O, but it's not like we're like a high-performance web server. We're actually not performing enough I/O for multiple threads to be worth it. And so this, for us, reduces the synchronization costs and actually ends up being faster, which is interesting. It also means that we're very careful about how we orchestrate like non-I/O compute. So, for example, we took all the compute work that happens in the resolver that's not I/O happens on its own thread. And we're very careful about how we schedule all the work that happens. This is the kind of thing that I think sounds very hard to do. And in truth, I'm probably not smart enough to figure it out, although Ibrahim is. But Rust as an ecosystem actually makes it relatively easy for us to manage the coordination of the resources and the sort of workflows within the project, which I think is pretty amazing. I mentioned before that we use a SAT solver, or sorry, I don't know if I mentioned that, but we we have to solve this NP-hard problem of trying to satisfy versions. So for that, we use a piece of technology called a SAT solver. And the SAT solver that we use is called PubGrub. It was originally created by Natalie Weizenbaum for the Dart ecosystem. And it's known in particular for having very good error messages. There's a big focus on trying to create very well-structured error messages. The crate we use in particular is called PubGrub RS, which was written by Jacob Finkelman, who's a cargo maintainer, and Matthew Peisenberg. And there's a lot of what I would consider like sort of classic and interesting performance optimizations in the PubGrub code base. This is the thing that's doing the actual constraint solving underneath the resolver. So for example, and I won't walk through these in details, small vex, so like storing small vectors inline on the stack rather than allocating. There's an arena allocator for package names. There's a lot of like ARC and RC for cheap cloning. But the cool thing, I think, in our like experience with PubGrub is there's also a lot of domain-specific optimization that needs to happen. So PubGrub is all built around like range operations. Often you're doing unions and intersections and complements. And we found that like optimizing those and running it against a really big, heavy UV workflow, again, sped things up like 4x. And the cool thing here is that PubGrub was originally written with an eye towards adopting it in cargo. That hasn't happened yet, but we adopted it, and we then went and took it and built this thing that a lot of people are using. So we now have like a very battle-tested SAT solver and resolver in the Rust ecosystem because it's being battle-tested here. And what we've been able to do, this is someone from our team, what we've been able to do is actually like profile a lot of interesting potential resolver performance optimizations on like the real problems that we face in the Python ecosystem. The last piece I want to mention here is I just want to talk about the cache design for a second. So a lot of what makes a package manager fast is in fact caching. And in UV, we tend to optimize for what I would call like warm operations. So often when you're installing a package on your machine, that's a package that you've like installed at some other point in the past. It might be installed in some other project. And the cache is really designed around trying to take advantage of that property. Like it's not, you might have a bunch of projects on your machine that use PyTorch. So what we store is this global cache of unpacked archives. In Python, distributions are shipped as zip files, but we actually don't store the zip files on your machine at all. So what we do instead is when we download, we stream and unzip directly into the cache. So the cache contains just a bunch of unzipped zip files effectively. And then when we install, we use either ref links, which is like copy on write, or hard links to link all those files into the user's environment. So the cache has this like global store of unzipped packages. And when the user needs to install it, like most installs are just hard linking a bunch of files into the user's project. It just looks like this on disk. Like this is the cache, right, from my computer. It's just a bunch of unzipped directories that contain lots of Python files and maybe some native code. And like this cache design, like none of this actually requires Rust. Like you could do this in any language, but I was just like thinking about it as I put together this slide. And it does require a couple things that I really didn't know how to do like a few years ago. So it requires, like async. It requires understanding like the zip format and how to operate on it at a byte level. It requires understanding like ref links versus hard links. It requires understanding how to implement those abstractions across different platforms. There's a lot of like implicit and accrued knowledge in actually building this piece of software. And I think the crazy thing for me is that I designed and implemented most of this part at least. And I learned Rust like 2 years ago, right, with like no systems programming experience. So Rust actually empowered me to build this, which to me is kind of mind-blowing. And I'm obviously not here to like sell you on Rust. I think you like Rust. But I am here to convince you that I think how we're using Rust at least is a big success story for the language and the ecosystem. Because I spent most of my career prior to about 2 years ago writing like Python and TypeScript. And I came to Rust having like very little idea what I was doing. And we've now built these software that's grown to hundreds of millions of downloads. And beyond Rust and UV itself, there's like this whole ecosystem of hybrid Rust Python tools. Pydantic, which I use as an example here, that's downloaded like 300 million times a month, I think. And that now uses a Rust backend with a Python front end. So this Rust-Python relationship is such that like one of the largest programming ecosystems in the world is now gaining access to more safe, reliable, high-performance software. And I only see that trend accelerating, and I hope it will if I have anything to say about it. Thank you very much.
Very cool.